This video is lesson 11.1 extension 2, and it's a continuation video of hydrogeology related with contour lines and groundwater flow direction lines. In this video we are going to see three different exercises where we are going to see how we can draw a proper contour lines. Also, we are going to see why it's pretty important to make the groundwater flow direction lines perpendicular to the contour lines, and also we are going to be talking about very interesting topic related with the scale of work and the measurements. Okay, then let's go to see it. In this exercise we are going to see how we have to do the contour lines in a groundwater flow map direction. Okay, as you can see here, the contour lines are parallels, and that's a very good example the how contour lines has to be. In this other side we have the contour lines where they are not parallel. Okay, that one is totally wrong. Okay, never do something like that. This one, it's a good example. Okay, it doesn't matter if the hydraulic gradient changes, because as you can see here, the hydraulic gradient in this area it's lower than the hydraulic gradient here in this area. Okay, that's pretty normal and can happen. Okay, for example, if we make a cross section here about these contour lines and we are thinking that the flux direction is this direction, okay, then this one it's up gradient and this one is down gradient. The cross section is going to be something like that. We are going to have an area where the water table has more angle, and then the angle goes a little bit more flat. Okay, then it's going to be something like this one. Okay, here the angle is bigger than here. Okay, and that's what it's indicating here. We have a higher hydraulic gradient than here. Okay, but this one doesn't make any sense. Okay, let's go to see the next example. In this example we can see how the hydraulic gradient is changing laterally. Okay, here the hydraulic gradient is higher than here. Okay, and also that can happen, and this representation it's okay. Okay, that one is good. Okay, for example, if we have a groundwater flow direction, something like this, okay, that map is good. But this one it's not good. Okay, because it looks like when we make the trend for the contour lines, it looks like that ones are going to cross each other. Okay, for example, this one is going to cross with this one here, and this one is going to cross with this one here. Okay, then these kind of things are totally wrong. Okay, lines has to keep parallels always. Okay, avoid these kind of things that the lines look is going to crash against the other line. Okay, let's go to see the next example. In this example we can see a mistake related with the crossing contour lines. Okay, that it's a really bad mistake, and I'm going to show you what it represents. Okay, let's go to make a cross section. That one is going to be the surface of the terrain, and the groundwater is going to be the blue line. Okay, in this case we have the groundwater table, and the groundwater table is doing something like this. It's a kind of wave. Okay, and at the vertical we have 2 points for the groundwater elevation, this one and this one. That is what it represents here. Okay, and we know that scenario it's pretty weird. Okay, and we don't want to see in groundwater flow maps the lines are crossing. That's a big mistake. Remember that the groundwater flow direction has to be always perpendicular to to the contour lines, okay, with an angle of 90 degrees, okay. As you can see in these draws, okay, 90 degrees for every line. How many groundwater flow directions lines you have to draw? It depends how many direction of the flux you are going to have in your map, okay, but you want to represent with these arrows the flux direction. Then I'm going to see enough arrows to demonstrate what is the flux direction in your map. In this case, the arrows doesn't represent any magnitude, and it doesn't matter how long they are, okay. It's something aesthetic on the map, okay. You want a clear map. Now let's go to explain why, if you are doing a line like that where the angle is not 90 degrees, it's a really big mistake, okay. At the next exercise we do something like this here, for example. It's a very big mistake, okay, where the angle is not 90 degrees. Let's go to see the next exercise. In this video we are going to be working with a real 3-dimension model. The goal is to understand how contour lines and flow direction works and what is the relation between these kind of lines. We are going to define a plane at the space based in 3 points with different height. The shape of the plane is going to be a triangle. Then we are going to drop a small ball from different points on the plane in order to see what is going to be the trajectory of the ball. As you can see, the trajectory it's always the same direction with respect to the north. This is because the trajectory is always perpendicular to the contour lines, and it is follow the maximum slope. In this case, the contour lines are equidistant and the plane is totally flat. The value of this contour line is 5 centimeters. I measure here and also here, and I measure the distance from the ground. This is the ground that is totally flat to the plane in these 2 points. Here is 7 centimeters, 9 centimeters, 11 centimeters. This one is 3 and 1 centimeters, okay. Then we can say for this contour line the value of the contour line is 5 centimeters above of a relative datum. The datum in this case is the ground, and that's a relative one, it's not an absolute one. As you can see in these contour lines, all the lines are straight. That's the reason, because the plane is totally flat. It's going to be different if the lines are making something like that. That is going to indicate that the plane it's not totally flat, it's curved, but it's not our case. The ball try to represent a particle of groundwater travel at the surface of the groundwater table. For example, if we have this particle here, what is going to be the trajectory, right? Then the particle is going to move from the highest point to the lowest point, okay? Always perpendicular to the contour lines, okay? In this case, that particle over there is going to travel in this direction, okay? Making always an angle of 90 degrees with the contour line, okay? This angle has to be 90 degrees in all the intersections, here, here, and here, okay? Now the question is, one particle from here can travel to here, The answer is not. One particle from here is going to travel in this direction, and one particle from here is going to travel in this direction. As I said already many times, the trajectory has to be perpendicular to the contour lines with an angle of 90 degrees. Okay? Then what happens if we draw a groundwater flow direction, something like this? We have to assume that the particle always is follow the maximum slope from the highest point to the lowest point according to the gravity law. Okay, if we make a representation something like that, this scenario goes against the gravity. Okay, that one is totally wrong. Okay, as you can see, the angle here is different than 90 degrees. At that one, it's not going to happen. Okay, then be aware that this kind of mistakes, because that one it's pretty common. I saw a lot of groundwater flow maps where the flux direction it's not 90 degrees, and that one it's not realistic. The only way you can change this situation, I mean, for example, if you want to move this particle here from here to here, is just to change the contour lines. Okay, in order to make that change, you have to, for example, pump water from here to create here a cone of depression, something like this, right? And then even that one bigger here, something like this. Sorry, something like this approximately. Okay, and then that's the only way you are going to move one particle from here to here. Okay, but then you have to modify the groundwater table. Okay, and as you can see here, I try to keep always 90 degrees. Okay, because that's the trajectory of the particle is going to follow. Okay, then let's go to move on to the next exercise. The topic of this exercise is going to be the relation between the scale of work, I mean the area you are working, and the measurements, the accuracy of your measurements. Okay, for do that one, we are going to use this map. This is the map that we was using at the lesson 11.1. Okay, where you can see here the scale of this map. This is an regional aquifer, and the area it's quite big. Okay, but we are going to be focused just in a very small area of this map. That is going to be this square here. We are going to be working between these two contour lines, the 51 and the 49 one. Okay, the units are in meters. The distance between these contour lines is 343 meters. Okay, and let's go to calculate what is the hydraulic gradient for this area from here to here. Okay, then let's go to suppose that that one here, this line here, sorry, I want to make a line just for a while. Okay, this one from here to here, let's go to suppose that that's the groundwater table, okay, and the distance here is 343 meters, and the distance here is 1 meter. Okay, for this draw there is no scale. Okay, as you can see, there are a lot of vertical exaggeration. Okay, because this segment from here to here try to represent 1 meter. Okay, but as you can see, this segment from here to here is 343 meters. Then the vertical exaggeration, it's quite big. Okay, then as we said in previous lessons, the hydraulic gradient, it's the difference between the groundwater elevation divided between the distance. Okay, the difference between the groundwater elevation is 50 minus 49, and the distance is 343 meters. Then the hydraulic gradient for this area is 0.0029. Okay, that is a quite low gradient, but it's very common in gravels and sand. Okay, then you have to be aware that the groundwater elevation in this area, okay, it's quite flat, because in 343 meters the variation is just 1 meter. Okay, now, well, one more thing I want to say here is just pay attention here, for example, for the groundwater elevation at each wall. You know, you can see that one, it's a decimetric precision. Okay, in this case, for example, is 53.7. okay, where 53 is the meters and 7 is the decimeters. Okay, then in this map we have an accuracy of a decimetric precision. Okay, and that's good because of the scale of work is really big. Okay, but let's go to see what happened when our scale of work is smaller. Okay, let's go to make a zoom of this area now. Okay, that's the square, and the distance for this square, that one is 100 meters by 120. Okay, to have an idea of the dimension of the site, and this site can represent, for example, an oil and gas field or even a gas station. You know, the contour lines, as I said before, is 50 and 49, and the groundwater flow direction is to the south. That's a very bad line. Okay, from groundwater flow direction is to the south. Okay, that one is better. And here we have a scale bar for a decimetric precision. Okay, that one is the meters, and the next number is the decimeters. Okay, and this one is for a centimetric precision. Okay, then let's go to suppose that we have 6 wells. Okay, P1, P2, P3, P4, P5, and P6. I put P because of the piezometer. Okay, but that one could be groundwater monitoring wells. Okay, all of these ones, 6 wells. Okay, and you have to think that if we go to the field, we don't have any information. Okay, we don't have these contour lines. Okay, these contour lines doesn't exist. We don't know what is the direction of the flux. We don't know anything. We go to the field, we install some wells, 6 wells, and now we want to make a characterization of this area. Okay, but you have to suppose that we don't have this information. Okay, we don't have that one, we don't have that one. I put that one to do the exercise and to to try to explain what is going to be the problems. Okay, as I said, the hydraulic gradient in this area is 0.0029, and that is a very low gradient. Okay, then let's go to think if we go to the field and we measure the groundwater table, okay, but we just take the meters. Okay, for example, in this case we go with the probe and measure the groundwater table, and we take the measurements in meters. Okay, and the result, when after we did all calculations with the vertical survey and with the groundwater table, then we calculate the groundwater elevation. Okay, and that one is going to be 49. Okay, because that's the result we are going to get, right? We have here 49, we have 50, and if we measure just the meters, we are going to have 49 for every well. Okay, the water table here is going to be 49, 49, 49 for every well. Okay, with that kind of information, we cannot do a groundwater flow map direction, right? That's pretty obvious, because if every well is 49, we cannot do anything. Okay, now let's go to think what happens if we take just the decimetric precision. Okay, for that one is going to be the first number, 49.5. okay, the first number here. In this case is going to be 49.4, 49.4, 49.3, and 49.3. okay, that's because this number is in this range. Okay, the second number, 49.4, is in this range. That's for the decimetric precision. Okay, and that one is in this range. Okay, now let's go to see what happened when we try to do the interpolation with these values. Okay, what is going to be the result for the groundwater flow map direction just with these values here. Okay, let's go to see it. When we do triangulation with linear interpolation, the result is this one. As I said before, these 2 points has the same elevation in decimetric precision, that is 49.3, and that 2 points are connected for the same line. Also the same with these ones, they are 49.4 and they are connected also with the same line, and also these two, okay, they are connected with the same line because it's the same elevation, 49.5, 49.5, right? Until here the lines are parallels. Okay, and it's pretty obvious that the groundwater flow direction could be something like this, right, from here to here. But what happened with this line here, right? That one is perpendicular to these lines. Okay, then the software made this interpretation. The software knows this line has to be, these two wells has to be connected for the same line. Then the software do something like that. Okay, in order to be connected these two wells with the same line, and to be parallel with these ones, because the contour lines has to be parallel, I'm going to create this kind of feature. That kind of contour line, it's not possible on groundwater. Okay, then if we want to do the groundwater table in our area with a decimetric precision, we don't have enough information to do that one. Okay, even because of the location of the wells, in this case the line, it's parallel to the general groundwater flow direction at the general map. Okay, let's go to see it. As you can see, the location of the wells are parallel, okay, to the contour lines in these both cases. Okay, but what happened if the location of this well, for example, this well, the location is here, and the location for this well is here? Okay, let's go to see, because that one is an interesting one. Then let's go to suppose. I'm going to remove all these ones. That we don't have, for example, this well, and we don't have, for example, this well. Okay, and this well now is located over here. For example, this well P3 now is here, and this well P2 now is here. Okay, let me put even something more here, something like that. Okay, then our interpretation, if we have these values, is going to be something like that. Going to change this one. Is going to be something like that. These points has to be together. Okay, because they have the same elevation. These two has to be together because they have the same elevation, and these two has to be together because they have the same elevation. Okay, that's very bad lines. Okay, this together, this together, and this together. Okay, something approximately. Okay, then in this case, if groundwater is moving from the highest point to the lowest point, in this case the groundwater is going to move something like this. Something like this, okay, from here to here. And we know that it's not the correct direction for this map. Okay, but because of the position of the wells, it's parallel to the contour lines. The result looks not really bad. Okay, but you have to be aware that it's a coincidence. Okay, if you have a decimetric precision in this area, you cannot make the groundwater flow map direction. Okay, now let's go to see what happened if we have a decimetric precision. I mean centimetric precision. Okay, centimeters. Okay, for the centimetric precisions, we have the second value: 49.57, 49.53, 49.45, 49.45. The point here for these two, they have the same value because they are at the same range. Okay, just for a while. From here, also the next one. Okay, we have these two wells in this centimeter. Okay, from 45 to 46. Okay, that's the reason, because we have the same value, and also happens the same for these two wells. Okay, 49.35, 49.35. Okay, now let's go to see what happened when we have a centimetric accuracy for the measurements. For the centimetric accuracy, the results are quite good in this example. We still having a little bit weird curves here, as you can see, because of the effect of triangulation with lineal interpolation. As you can see here, the line is doing something like this. Okay, but the result is not bad. Okay, then in this example, if we have the centimetric precision, we can draw the groundwater flow map direction. Okay, the lines are pretty good, and we can make the arrows. Okay, and the result is going to be good. Okay, but we have to be aware that if the hydraulic gradient is even lower than 0.0029, if we are using centimetric precision, we are going to have troubles, and we can miss the groundwater flow direction. Okay, we can provide our wrong groundwater flow direction. Okay, let's go to see why. as you can see, when we are using a centimetric precision, we are assuming that these two wells, they are at the same line. Okay, but as you can see, that one is not true, because this point, it's a little bit more closed. Well, if you see in millimeters, that one is 55 and this one is 52. Then the wells are not located at the same point. Okay, but when we are using centimetric precision, we are assuming that both are located at the same point, at the same line, and that's not true. Okay, and also it happens with this one here. Okay, let me remove. Here there is 59 and here is 52. Okay, but when we are using a centimetric precision, we are saying that both has the same value. Okay, and that's not true. Okay, we are making a line and we are saying both are at the same point. Okay, but that's not true, because that one is 59 and this one is 52. Okay, and that can change the groundwater flow direction. Okay, then my recommendation, when you are working in an area where the water table it's pretty flat, the best way to measure the groundwater table is with millimeters. Okay, because you are not going to see what is the real groundwater elevation for every well until you do all the calculations. Okay, maybe you are thinking the area it's quite flat, the topography is quite flat, but you can't trust with that one because the topography is really tricky. Maybe you are thinking the topography is pretty flat, and then the difference between one point and the next one could be 1.5 meters or something like that. Okay, then if you are always measured in millimeters, you are going to avoid this kind of mistakes. Okay, because you have to think that if you are measured in centimeters, okay, the groundwater table in centimeters, you can miss 9 millimeters. Okay, 9 millimeters, you can miss 9 millimeters. And also, if you are doing the vertical survey, and also you are doing the vertical survey in centimeters, you can miss also 9 millimeters. Okay, and if you plus 9 is going to be 1.8 centimeters of error. Okay, and if the groundwater table is very flat, that it's enough to change the groundwater flow direction. Okay, and maybe you are thinking the groundwater flow direction in this area is something like that. Okay, something like that, with the flow direction like this, but maybe the contaminant is moving in this direction, and you make a wrong interpretation of the groundwater flow direction because you measure just in decimeters or in centimeters. Okay, now to finalize this exercise, let's go to see what is the result for the millimetric accuracy. Okay, as you can see, for the millimetric accuracy, the precision it's really good, and the groundwater flow direction it's like the general map. Okay, that's really good. We don't have any weird thing at the control lines, and that's really good. Okay, I would like to say something more related with interpolation. I know I said that one at the previous video, but this is it's very important that it is okay if I'm repeat again the same thing. Okay, remember that the software it's not a hydrogeologist. Even it's not the most important part of the interpretation. Only the professional can provide interpretation, and the professional is the most important part of the process of investigation. Okay, the software is a tool to help the professional to take decisions, but it is not a final solution without professional validation. Okay, the problem is it's a very common mistake that companies, they put the values inside the software to interpolate the contour lines, and they make the maps with the results that the software provide them. Okay, and what happened, you can find groundwater flow maps directions with something like this. Okay, because there is no hydrogeological interpretation behind. You know that one, the contour lines here is going to be like this, here is going to be something like this, here is going to be something like this, but here is going to be something like this. And you know that one never is going to happen. Okay, but if you put the values in the software always is going to provide you a result. That's the problem. But the software didn't know if that result is good or no. That's the professional decision, and that decision is based on your knowledge and on your education. Okay, a professional can give a solution without software, but a software never is going to facilitate a solution without a professional. Okay, I don't need the software to interpolate the contour lines. I can do by hand. I don't need the software, right? The software is just a tool that is going to help me to provide more information. Then I have to take the final decision. Okay, I'm pretty sure this map is totally wrong, because even those lines are good if you have just the decimetric precision for that area, that is 120 by 100 with hydraulic gradient of 0.0029. You cannot work with a decimetric precision. Okay, and that one also apply for a centimetric precision. If your gradient is even low, you cannot use a centimetric precision. You have to use a millimetric precision. And I'm not going to say you can use something like nanometric precision, because you cannot do that one, but you can do that one in millimeters. Okay, I do the vertical survey and the measurement of the groundwater table with a millimeters always, and it's not difficult. Okay, then to finalize, be aware what is your scale of work and what kind of measurements you need for that scale. Okay, if you are working in a really big area, you don't have to be that accurate. But if you are working in a very small area, like 100 by 100, where you have sand or gravel, you have to suppose the water table in that area is going to be very flat. Okay, and if you are taking the measurements in centimeters, you can make a wrong interpretation of the groundwater flow direction. Okay.